In this lesson, we are going to learn about strings. A string is simply a sequence of characters. For example, hello is a string, cat is also a string, and 12,345 can also be a string. A string is not limited to letters. It can contain uppercase and lowercase letters, numbers, spaces, punctuation, and symbols. For example, hello contains letters, followed by an exclamation mark. Each character has its own position in the string, and the order of the characters is important. So remember, a string is an ordered sequence of characters, and those characters can include letters, numbers, spaces, punctuation, and symbols. Now let's see how a string can be broken into individual characters. Here we have the string cat. It contains 3 characters, C, A, and T. Each character has its own position in the string. These positions are called indexes. In many programming languages, indexing starts from 0. So, C is at index 0, A is at index 1, and T is at index 2. This allows a program to access and process each character individually. So remember, a string is a sequence of characters, and each character can be identified by its index position. Now let's see how a computer represents a string. Here we have the string cat. First, the string is separated into individual characters, C, A, and T. Each character has its own ASCII decimal code. C has the code 67, A has the code 65, and T has the code 84. These decimal codes can then be represented in binary. So, inside the computer, the text cat can be represented as a sequence of binary character codes. This is the important idea. A string is made from characters, and each character is represented using its own character code. Now let's understand why character order is important. Here we have the string cat. Its characters are CAT. Their ASCII decimal codes are 67, 65, and 84. Now look what happens when we change the order. Instead of CAT, we arrange the characters as TAC. The codes are now 84, 65, and 67. The same characters are being used, but because their order has changed, the resulting string changes from cat to TAC. So remember, a string is an ordered sequence of characters. Changing the order of the characters changes the string. Now, let's learn how a program moves through a string, one character at a time. This process is called traversing a string. Here we have the string data. The first character, D, is at index 0. Next, A is at index 1. Then, T is at index 2. And the final A is at index 3. The program starts at the beginning and visits each character in order. DATA. This allows the program to examine or process every character individually. So remember, traversing a string means moving through the string, one character at a time, from start to end. Why do programs traverse strings? Because sometimes we need to examine every character individually. Here we have the string hello. The program moves through it. HELLO. Once each character can be examined, the program can perform many useful tasks. It can search for a particular character, count letters or digits, validate user input, or even encrypt text. Programs can also analyze passwords, change letters between uppercase and lowercase, analyze text, and convert characters into numerical codes. So traversing a string gives a program the ability to examine, understand, and process each character one at a time. Now, let's learn how to convert a character into its numerical code. For this, we can use the ORD function. The ORD function takes a character and returns its decimal character code. For example, lowercase c has the decimal code 99, so ORD c returns 99. We can do the same with other characters. Uppercase A gives us 65, B gives us 66, and C gives us 67. So remember, ORD converts a character into its corresponding numerical code. Now let's convert an entire string into character codes. Here we have the word dog. First, we look at each character separately, DOG. Then, we use the ORD function to find the decimal code for each character. For D, ORD returns 68. For O, it returns 79. And for G, it returns 71. So the string dog can be represented by the decimal codes 68, 79, 71. This shows us that a complete string can be converted, one character at a time, into a sequence of character codes. Now, let's see how we can traverse a string and convert each character into a code. Here we have the string cat. The string contains 3 characters at indexes 0, 1, and 2. A loop starts at index 0 and visits each character one at a time. At index 0, we have C. Using ORD, C becomes 67. Next, at index 1, we have A. A becomes 65. Finally, at index 2, we have T. T becomes 84. So after traversing the complete string, we get the character codes 67, 65, 84. This is how a program can move through a string and process each character individually. Now, let's look at the reverse process. We can convert a numerical code back into its original character. For this, we use the CHR function. Here, our decimal code is 100. We pass this number into CHR. The function converts the code and returns the corresponding character. In this example, CHR 100 gives us lowercase d. So remember, ORD converts a character into a code, while CHR does the opposite. It converts a code back into a character. Now let's see how we can reconstruct a complete string from numerical codes. Here we have 3 decimal codes, 67, 65, and 84. We use the CHR function to convert each code back into a character. 67 becomes C, 65 becomes A, and 84 becomes T. Now we have 3 individual characters, CAT. When we combine these characters in the correct order, we reconstruct the original string, cat. So remember, codes become characters, and characters can be combined to build a complete string. Now let's understand an empty string. An empty string is a string that contains no characters. It is written using 2 quotation marks, with nothing between them. Because there are no characters, the length of an empty string is 0. But be careful, an empty string is different from a string containing a space. A space may look empty to us, but to the computer, a space is still a character. So a string containing 1 space has a length of 1. Remember, an empty string has 0 characters, while a space is a real character. Now let's see how we can build a string step by step. We begin with an empty string. Its length is 0. First, we append the character C. The string becomes C. Now the length is 1. Next, we append A to the end. The string becomes CA, and the length becomes 2. Finally, we append T. Now the complete string is cat, and its length is 3. This process is called appending. Appending means adding a new character to the end of the existing string. So remember, we can start with an empty string and build a complete word, 1 character at a time. Now let's see how we can build text from character codes. Here we have 3 decimal codes, 67, 65, and 84. We process these codes, 1 at a time. First, we take 67. Using the CHR function, 67 becomes the character C. We append C to our empty string. Next, 65 becomes A. We append A, and our string becomes CA. Finally, 84 becomes T. We append T to the end, and our final string becomes cat. So remember, we convert each numerical code into a character, and append each character to the string, 1 at a time, until the complete text is built. Now, let's work through another example. This time, we are going to build the word dog. We start with an empty string, with a length of 0. Our first character code is 68. Using CHR, 68 becomes the character D. We append D to the string. Now the length is 1. Next, we take code 79. CHR 79 gives us O. We append it, and the string becomes DO. Finally, code 71 becomes G. We append G to the end, and now our completed string is dog. So the codes 68, 79, 71 can be converted into characters and combined to reconstruct the word dog. Now let's look at the complete journey of a string. We start with the word cat. First, during encoding, the string is separated into individual characters, C, A, and T. Each character is converted into its decimal code. C becomes 67, A becomes 65, and T becomes 84. These numbers can then be represented in binary, which the computer can store and process. Now we can reverse the process. This is called decoding. The binary values are converted back into decimal codes, then back into characters, CAT. Finally, the characters are combined, and we get the original string, cat. So remember, encoding converts text into computer-readable codes, while decoding converts those codes back into readable text. Now let's see how a string is actually represented inside a computer. To us, the word hello is easy to read, but a computer does not store these letters directly. First, each character is converted into a numerical code. H becomes 72, E becomes 69, L becomes 76. The next L is also 76, and O becomes 79. These numerical codes are then represented in binary, using only zeros and ones. The binary values can be stored in memory and processed by the computer's electronic circuits. So remember, we see hello as text, but inside the computer, the characters are represented by numbers and ultimately stored and processed as binary. Here is an important point to remember about strings. A common mistake is to think that an entire string has one single character code. For example, the string cat does not have one code such as 6784. Instead, a string is made up of individual characters, and each character has its own code. For cat, C has the ASCII code 67, A has the code 65, and T has the code 84. So the string is represented by a sequence of character codes, 67, 65, 84. For the exam, remember this important rule. A string is a sequence of characters, and each character is represented by its own character code. Now let's look at what a string can contain. A string is not limited to letters. It can contain uppercase letters, lowercase letters, numbers, spaces, punctuation, and even special symbols. For example, ABC is a string. 123 is also a string, and a string can contain spaces and punctuation too. Now there is one important difference to remember. An empty string contains no characters at all. Its length is 0, but a string containing one space is not empty. A space is still a character, so its length is 1. So remember, a string can contain many different types of characters. Always check what characters are inside the string, and check its length. Let's finish this lesson with a quick summary. A string is an ordered sequence of characters. Each character has its own numerical code. For example, the string cat contains C, A, and T. Their ASCII decimal codes are 67, 65, and 84. These codes can then be represented in binary, which the computer can store and process. We can use ORD to convert a character into its numerical code, and we can use CHR to convert a numerical code back into a character. We can also traverse a string, visiting each character, one at a time. Remember that indexing usually begins at 0. An empty string contains no characters, so its length is 0. But a space is a real character, so a string containing one space has a length of 1. And finally, we can build strings by appending characters one at a time. The key idea to remember is, a string is a sequence of characters. Each character is represented by a code, and inside the computer, those codes are ultimately represented in binary.